Okay, so let's get started. Our next speaker is Dr. Samuel Khuvis. He's a scientific application engineer at the Ohio Supercomputer Center. He received his PhD in applied mathematics at the University of Maryland, Baltimore County in 2016. Before joining OSC, he was an HPC software engineer at Paratools. He's interested in performance analysis and optimization, scientific computing, and parallel computing. Today, we will be talking about optimizing AMBER for device-to-device GPU communication. So let's welcome Sam.
So thank you. So this talk is about, so you speak into it, okay. All right, this talk is about optimizing AMBER for device-to-device GPU communication. This is really more of a test case showing some of the benefits of using GDR and demonstrate the work that I did to figure out how to implement it and how easy it is to implement. So I'll start off by giving an introduction to AMBER, to MBAPS2 GDR, and then talk a bit about the experimental setup, the performance analysis that I performed to figure out how to modify the code to use GDR, the code changes that I made, and go over some results. So giving an overview of AMBER, it's one of the most popular, widely used molecular dynamics simulation codes out there. It supports two types of solvents, particle mesh Ewald, PME, and generalized Born implicit solvents. GPU support was added in version 11, and now we're in version 22, so it's been around for a while, but multi-GPU implementations in AMBER were added in, I think, AMBER 16, but it's done through the CPU buffer. So communication is done by passing data from GPU memory to host memory, and then performing MBI communication between them, and then passing it back to the GPU. So a bit about GPU support in MPI. The ability to pass in device buffers was added to MVAPIC in 2011, and soon after in OpenMP in version 1.7.0. So the way it works is that if the appropriate hardware and software is available on your system, then communication can be performed directly on the GPU without any host transfer. So I have a little diagram here of kind of what our system looks like at OSC. So we have two CPUs that have each have their own memory, and they're connected to a GPU, each with their own memory, and then you have a network connecting them. So if you have the appropriate hardware and software, the GPU can directly communicate through the network from one GPU to another GPU. But if that's not available, then we have to do inter-process communication and host-to-device transfer. So we'll copy the data from the GPU, then onto the CPU, and then the CPU will communicate to the other CPU, and then back. So that adds more data copying. It will slow down performance. So if possible, we want to try to modify our codes to do the direct GPU communication with MVAPIC2 GDR. So as I said, the MPI libraries have supported this for a while, but the hardware has really only started to be available at sort of academic HPC centers in the last few years. And as a result, many scientific and research codes have been slow to take advantage. So as another example, another very popular computational chemistry code is GROMACS, and they just added GPU communication in their release in 2022. So now I want to talk a little bit about the experimental setup, the experiments that I ran. So I took the sort of the standard set of benchmarks in Amber 20, in the Amber 20 benchmark suite, and I took 4 different particle mesh Ewald test cases: cellulose, factor, IX, Jack, and STMV, and then 2 generalized Born myoglobin nucleosome. One note to point out is that on top of the 4 different PME experiments, each of those PME experiments was run with 2 different statistical ensembles: NVE, where the total number of particles is constant and the total energy and volume are conserved, and NPT, where the pressure and temperature are conserved. So in general, you'll see that the NPT is going to be slower and more expensive compared to NVE because of the need to conserve pressure and temperature. So next, a bit more about the system bits are where we ran on. The part of the system that these tests were run on were 48-core Cascade Lake nodes. They each have 2 NVIDIA V100 GPUs. We ran with 2 processes per node, so each process had its one GPU that it communicated with, and tests were run on 2, 4, and 8 nodes. The nodes are connected with Mellanox EDR InfiniBand. It's 100 gigabits per second. And we tested with 3 different MPI implementations. The just sort of vanilla MAPIsh 236, and then 2 MPI implementations that are CUDA aware, meaning that they can perform GPU to GPU communication. That's MAPIsh 2 GDR 237, and then the HPCX OpenMPI 3.1.6. So I'm not, a computational chemist. I came at this just from a performance analysis perspective. So the first thing I did was I profiled the code with the map profiler, and immediately what I saw was that most of the time was being spent in MPI communication, in particular, in communication. So part of that is in MPI communication and in all-reduce, and then also in device to host and host to device communication through CUDA mem copy. And I think that accounted for 70% of the total runtime. So that view is, it just looks at, you have here the just a list from the most expensive subroutine and going down to less and less time being spent. So next I looked at a call stack to see where that all reduce was being called from. And you can see it's being called in this PME force mod subroutine, and inside of that there's a GPU all reduce, and in there's a subroutine that's calling CUDA mem copy and all reduce. So it's all happening inside of this GPU all reduce subroutine or function. And that's just that GPU all reduce communication is accounting for about 60% of the total runtime. So here's the originally in the original code what the GPU all reduce function was doing. It was doing a CUDA mem copy from the device to the host, then doing an all reduce between host memory, and then copying the result back from the hosted device. So kind of that first approach that I mentioned earlier. So to change it to use MPI to use MVABISH to GDR, it was really just 5 lines of code, very simple. Remove the copy at the beginning, just do the all reduce directly on the device. We need to device synchronize to make sure that the device is up to date, but otherwise, really all you need to do is an all reduce. And then just for the way that Amber runs, we need to do a device to host copy because it assumes that the device and the host are in sync. So that was very simple 5 lines of code, as I said. This was folded into, we missed the deadline for Amber 22, but it's in their code base now. And actually, the changes to the build system that were required to implement this were bigger than the actual code changes. I think 15 lines of changes to CMake to get it to work. So now I want to give you an idea of some of the results. So I took one of the benchmarks, the JAC benchmark, and I have here results with, so red is the original code, unmodified using just the vanilla MVAPage 2. Then I tested the modified code with the device buffer communication, with again just with the MVAPage, and then I tested the modified code with HPCX and MVAPage 2 GDR. So what you see is that going from the original code to the modified code in orange, even with the MVAPage gives you a slight improvement in this benchmark. And then, but the real improvement comes from going from non-CUDA aware to CUDA aware, going directly communicating between GPU device buffers without the CPU. So to give an overall summary of the performance across all the benchmarks, I just took an average across all the different node counts and benchmarks. And so what you'll see is that going from the original code to the modified code, you see some slight improvement, about 5%. Going from that to OpenMPI, you get 22%, but the best performance is with GDR. That gives you a 36% improvement over the original code. What's more impressive is if you look specifically at the PME, the explicit solvent benchmarks, you see an even bigger improvement. So there, using GDR, you can get an 84% improvement over the original code. So those results were, I think, really impressive. There were a few results that we didn't expect. So there's one case, the myoglobin benchmark case, where the performance of GDR degraded compared to the reference and modified code with MVAPage 2. And that's something that we haven't been able to figure out why that's happening. And then we also had two benchmarks, the cellulose and STMV benchmarks, where for some reason, just with MVAPage, vanilla MVAPage, going from the original code to the modified code, again, showed some performance degradation. And yeah, the other thing is that the nucleosome case showed good scaling, but a lot of the other cases showed poor scaling when you go up to higher node counts. So to summarize, we did some profiling and we found that the most expensive functions in our benchmarks were in the GPU reduce function, particularly the MPI reduce and the CUDA mem copy. We did some very straightforward modifications to the code to do direct GPU buffer communication to reduce the hosted device communication. And overall, we saw 36% improvement in performance over all benchmarks, and particularly for the PME subset, we saw an 84% improvement. And although the scaling wasn't very good for the tests we ran, we believe if we pick a better test cases that you can see better improvements in some of these cases, like long time scale, molecular dynamics, or free energy calculations. So this work was based on a paper from PERC. This is it if you want to take a look and see more information. I'm taking questions.
Do you have any questions?
Yeah, so you showed a slide which where your modified code had a CUDA mem copy to the host. Could you explain why you needed that if the data was on the device? Yeah, that.
So
Like in the second one. Yeah.
yeah. There's Amber also does computation on the CPU, so it needed to synchronize the data on the host and the
Oh, so it
GPU.
does both. Okay.
Yeah.
Okay. Okay, that
It's
makes
not
sense.
completely on the GPU.
Okay, okay. Thank you.
Yeah. So how much time was spent on this device to host memcopy compared to the total time? Do you know the percentage in the modified code?
The modified code.
Is it like more than 10% or like even below that?
I don't know the number off the top of my head, but
Okay.
but considering it's about about half, or my guess is, if I had to guess, I would say it's probably still 30-40%.
Okay. Thank you.
Yeah.
Can you do that in a non-blocking fashion? Do you know how much of a computation the DPU, I mean, the GPU and the CPU is spending on separate computation path?
I can't answer that now, but I think it's a good question.
Okay.
I think it might be possible. Yeah.
Let's thank our speaker again. Thank you, Sam.